Right to go. Well, good afternoon, everyone in the room, and also to the very many people that we have online. My name's Adrian Pano. I'm the Director Major Projects within the Melbourne Energy Institute, and welcome to today's first of a series seminar. Before we begin, I'd like to acknowledge that we are gathered here today on the land of the Wurundjeri, Woiwurrung and Boon Wurrung people who've been custodians of this land for millennia. And pay my respects to their elders, past and present, and with many people online. Many of those will be on different lands, and if you wish to pay your respects as well, by all means. Our seminar today is the first, as I said, of a series. Last year, many of you will have participated in the series where we looked at the commodities, the substances we get energy from, whether they be the more traditional fossil fuels or the emerging and no longer emerging renewable energy that we use, and some that we may use in the future. The series this year is focusing on the electricity supply chain, and obviously a great deal of interest in electricity and electrification. There are some parts of the Australian sector that are difficult to electrify, but the vast majority, electricity will be the core of that energy supply. And so this year we'll focus on all aspects, and not only, of course, on the technologies, but the markets, and then the community engagement and where electricity changes people's lives, where it may change the way that industry operates as well. And we'll cover that in this series. I have. Yeah. Not live. Okay, I'll press an arrow. No, I won't press an arrow. Bear with us. Here we go. I'll use the mouse. So, an overview of how electricity is generated through to how it reaches the customer from very much an engineering perspective, through to then the details of the network, wholesale markets, financial markets, and ultimately retail markets, covered by different speakers who are experts in that field. The emerging system of distributed energy, and again, ranging from domestic residential through to much larger energy generation and consumption. And finally, the communities that have, in some cases, evolved because of new ways that we can generate electricity, and particularly around microgrids. And so that'll cover us right through to the end of the year. Today's speaker, then Chris Mock, is going to start that whole series and give you the background and really the framework within which this whole new energy system operates. Chris is the Manager Engineering Strategy at the Australian Energy Market Operator, AEMO, and leads the strategy team. The team has developed AEMO's engineering roadmap to 100% renewables, and it also is addressing the engineering actions that are really required to allow the NEM to operate in that new regime. Holds a Bachelor of Electrical Engineering and a Master of Energy Systems, and some of you are also graduates of the same courses here, and has 15 years of experience in engineering analysis, product design, and roles across energy, water, and agriculture sectors. So thank you, Chris. Over to you.
Thank you very much, Adrian. Hi, everybody. Thanks for joining us here today in person or online. Everyone here today that I can see, you're my litmus test for level of interest, level of depth. So if I go off topic, then feel free to use your phones. If I'm doing well, feel free to give us a smile. So look, yeah, really nice to be back here at University of Melbourne. I attended here probably best part of 10 years ago now. Fair to say things have changed rather a lot. But here today to give you, I guess, the 101 on our generation to consumer view of the electricity system. It's impossible to do that in the time that we have available. So instead, I'll give you some sort of selected highlights from my own experience with a rough alignment to the topic we have today. So it's sort of, as discussed here this afternoon now, my role here at AEMO is the newly established Manager of Engineering Strategy function. Our primary output is this engineering roadmap to 100% renewables. And I've drawn a lot of the content from this presentation from that body of work. So today we'll speak a little about the basics, some of the concepts that I'd like to speak about, what AEMO does, and I'm actually going to do this backwards because we're going to start with consumers and we're going to end with generation. That's because consumers are sort of forefront of what we do at AEMO, despite us having a very large scale end of town bent as an organisation. We do and are rapidly beginning to consider the smallest of small as perhaps the largest of large in terms of impact to the system. We'll save a fair bit of time for Q&A, so please have a think if you've got any questions that come up. Happy to take any and every question. So about AEMO, many of you will be familiar with what we do as an organisation. We're a member-based, not-for-profit organisation. It's sort of partly owned by government, partly owned by the market participants themselves. We hold a variety of roles across the country. On the East Coast, we're the market operator, system operator, and system planner for the National Electricity Market, the NEM. We're also independent market operator and play a number of roles in the wholesale energy market in Western Australia. We also play a number of roles in gas. I'll be speaking primarily about electricity today, but certainly gas is a highly sort of interconnected and relevant part of this discussion. So to start, I guess, is a little teaser of the energy transition as we see it is well underway. We've got these commitments across all Australian governments at a Commonwealth level, at a state level, committing to adopt this target of net zero emissions by 2050. And that's driving everything we do at the moment. Coal-fired electricity is a challenging thing to accommodate with a net zero mandate, and it is retiring. That is both due to the age of these plants, as well as the market incentives that are being sent to them, in part due to the emissions targets that have been adopted and the policies thereof. That retirement is happening far faster than anticipated, and that presents us with a very, very rapid transition away from the plants that have been essentially the backbone of our system for 100 years or more. But that's not the only part of the transition. We've got the consumption side of the equation rapidly evolving as well. Household and business electricity consumption forecast to nearly double by 2050. And 2050 might sound like a very, very long way away, but we're almost 2025. That's 25 years for us to double the energy delivery capacity of the system. And we do see that need for urgent investment so that we can continue to enjoy this secure, reliable, affordable energy in line with the National Electricity Objective. And as an organisation, we do a lot of work planning for this transition. And we see that renewable energy connected with transmission, thermal storage backed up with gas, it is that lowest cost pathway to supply electricity to homes and businesses in this new net zero era economy that we're moving towards. So I'll touch on that a little bit more during this presentation. It's just some facts and figures here from our draft 2024 integrated system plan. I really just put this up to point out how enormous these numbers are, and what the challenges ahead of us and what that opportunity is ahead of us. 7-fold increase of grid scale wind and solar by 2050. A huge amount of that happens by 2030. Distributed, so rooftop solar PV increasing 4-fold. Given that where we are today as a country in terms of rooftop PV penetration, something around 1 in 3 households have rooftop PV, and we're saying it's going to increase fourfold. So, you can see the scale of this. It's unprecedented anywhere else in the world. And so how do we think about that as a sort of paradigm shift to what is fueling essentially our energy system? I won't go through each of these. We've got some other slides to look through, but please just take this as an indication that the transition is happening. It is happening fast, and it is happening large. And so the role of the grid changes in accordance with that rapid pace. Historically, we've had this sort of one-way system. We've had energy is generated by large centralized generation, typically near centres of coal production. It essentially flows downhill like water through the transmission system, through the distribution system into homes and powers your homes and businesses. But now we're at this point where we've got 1 in 3 homes with rooftop PV. So it's a two-way system. It's a fundamental shift to what we've been doing for 100+ years. It's still largely, though, within that operational envelope of the system. The system still works. It's able to flow in 2 directions, particularly in the distribution system. And it's largely predictable because we know when the sun comes up, we know where the clouds are, we can model this, and we can predict what photovoltaics and what wind are going to do to a degree. In the future, essentially the future is now, as far as I'm defining this, the intelligent participation at all levels of the system, from behind the meter through to gigawatt scale plant. It's adding to that sort of complexity, it's adding to the opportunity, but it isn't necessarily catered for by today's systems and processes. And so that's a core part of this transition. There is an ongoing value for transmission, as well as the need to modernise our distribution systems to accommodate for these two-way flows. And AEMO's role as well continues to evolve, and we continue to have our focus on consumer interests under the National Electricity Objective, which does speak to that, long-term interest to consumers for, price, security, reliability, and so forth. So that actually doesn't change, other than the recent addition to emissions to that equation. So we do now, as part of our role, have to consider emissions in the decisions that we make. So in that note, we're going to do this backwards. We're going to start with consumers, and we're going to move to generation. So some charts here. These are sourced predominantly from our draft 2024 integrated system plan. The step change scenario that we're referring to here was decided by a so-called sort of Delphi panel of experts as the most likely of the scenarios to eventuate. That doesn't mean it's the only scenario we model. It's the one I've chosen here today to be representative of the most likely pathway through our scenario map. And there's some interesting characteristics of these charts. So on the left, you can see a breakdown of where we see total NEM electricity consumption going. The little trick here is that black solid line in the middle is so-called operational demand. So that is what the grid is delivering. Everything above the line is being generated by on-site generation, be that rooftop PV, be that larger sort of on-site generation with and the top red section there represents demand that does not happen due to energy efficiency, which is a really key part of this picture. But what strikes me is that there isn't really any growth visible in that residential block below the line in terms of the energy that's supplied by the grid to consumers. It is growing, but fairly steadily. The business and industry portion, that is what is driving the growth in underlying demand in the national electricity market. There's a number of reasons for that, and that zooms in on the right-hand side there. So certainly growth in business over time is 25 years, and we would certainly hope that the economy does grow over that time and the business grows accordingly. But there's also some other wedges there that haven't existed in the past. Electrification of business, industrial processes is a way for them to move away from gas and meet their own carbon reduction commitments. Electric vehicles, obviously a relatively small wedge today, but growing enormously. Some of these other new industries, such as hydrogen, and you can see that there's an element of hydrogen above the line and below the line there. So there's that role for consumption from on-site generation to create hydrogen. So I mean, this is a complex picture, but I think that there's some quite interesting things to take home from that, particularly around that growth of business and industry. So sticking with the consumer lens here, so consumer energy resources. These are, I guess, otherwise known as distributed energy resources. Consumer energy resources is a term that's sort of been adopted across the Australian industry recently to just reflect who it is that owns these and who it is that is going to make the decisions around them. So this is a stack of the forward-looking capacity of the NEM. So this is the installed gigawatts of generation capacity. Obviously, it's not sunny all the time. It's not windy all the time. This won't be generating all the time, which is fairly lucky because we've got a sort of 30-something gigawatt peak system, and we're getting 300 gigawatts of capacity by 2050. Again, the black line on this chart is important. It shows that dispatchable capacity. It says how much of it can be essentially controlled to meet the needs of the fluctuating demand on the system. Everything above that line is, if not passive, then driven by fluctuating forces such as weather. But that's what strikes me about this is this 4 times increase in rooftop and distributed solar. And what can that facilitate? That's the largest wedge of, on this chart of installed capacity. And the opportunity that provides is at the bottom underneath that line, which is this coordination of consumer energy resources. So what I mean by coordination is that these systems are very small in aggregate. I have 3 kilowatts on the roof of my house. That's fairly much a rounding error in the system of the NEM. But what if you have 100 of them? What if you have 10,000 of them? What if you have multiple millions of devices that are all there generating and intelligent in their behavior? Because these are power electronic devices with microprocessor control and communications and internet connectivity and so forth. So what could you do with that in aggregate? Well, certainly the opportunity exists for consumers to enroll these in the likes of virtual power plants so that they can operate essentially as a single entity, participating in markets, earning additional revenue for those consumers. And let's be honest, 0.2 gigawatts, 200 megawatts today, that is not a huge number in terms of our estimate of coordinated CER from a grid perspective. What can be dispatched by a market operator, system operator like ourselves in order to match demand. But by 2030, we start to see an uptick. We start to see 3.7 gigawatts. Now, that doesn't mean that's immediately going to happen. That means that's something that we feel should happen and that we need to make happen. But right today, those systems aren't necessarily in place to effectively coordinate that. But look to 2050, 37 gigawatts. That's 48% of the dispatchable capacity that we're expecting to come from small-scale systems. And so that's a really exciting opportunity for consumers. It's also a really complex challenge to solve because no longer are you essentially picking up the phone to a multi-gigawatt generator and saying, hey, there's an emergency, you need to do this, please. You can't do that to hundreds of thousands of individual homes and businesses. You have to consider how that signal is getting to them. Is it getting to them through the internet? Is it getting to them through the NBN? We really do start to have to consider at 48% of dispatchable capacity, what are the factors that are going to influence that coordination? So this is one of the outcomes that we see of distributed PV, rooftop PV essentially. I've given up updating this chart. It's out of date, 1st of October 2023. It changes so rapidly that the records fall, month after month. And so as of sort of December in 2023, we've already seen periods where rooftop solar, so homes and businesses with panels on the roof, have met the entire underlying demand needs of South Australia. I'll sort of pause there because that is unheard of anywhere else in the world to have a gigawatt scale, region of a power system powered entirely by rooftop PV. It wasn't necessarily in front of mind for the designers of those systems when they were coming up with these, even 10, 15, 20 years ago. It wasn't expected that they would be the only source of energy that is powering South Australian homes. So this has already happened. We talk about over the years the duck curve of what the challenge of sort of sun coming up during the day, eroding the need for operational demand from the grid. and then peaking rapidly as the sun goes down, and the ramp of generation that's required to meet that. I mean, what you see here, this duct is underwater. Like, the duct is submerged at this point. So how do we deal with this from a grid operations perspective? Now, currently, you can see a lot under that line, and what we mean by demand profile under the line here means there's excess demand in South Australia to serve the needs of South Australian consumers, and it's being exported to Victoria. And in fact, that's the only way we can operate the South Australian system at the moment, is at these very high rooftop PV penetrations. We can export to Victoria in order to retain, in this case, the grid scale generation that is needed to stabilise that system, and is needed to provide that protection should rapid unexpected cloud cover come through, should there be a power system event that causes those units to trip offline. In aggregate, rooftop PV is almost always the largest single contingency in South Australia during the day. So that means it is the largest generator from our perspective. And you do see, while obviously an effect to the power system doesn't have to trip every single plant offline, and a voltage or a frequency disturbance that would affect maybe your household inverter might not affect one down the road, but in aggregate, with a large enough disturbance, we do see systemic shake off of rooftop solar, and if that's in the hundreds of megawatts to gigawatts, we've suddenly got a very sharp change to manage as system operator. So the interesting line here, as well, is the fact that we've got this sort of dark green wedge at the bottom of the screen representing gas generation. And currently there's a limit in South Australia that's a constraint that is applied, such that to a minimum of 2 gas generators must remain on at all times. And that's for a number of reasons. That's to maintain a secure system is the broad concept, but it's to support system strength and inertia in the Adelaide area, voltage support in the Adelaide area, as well as providing that fast ramping capability for the afternoon when that gas is suddenly needed again, as you can see here around sort of 4 or 5 o'clock. While the wind is carrying some of that demand, gas is carrying the rest. So what does that mean? What is minimum operational demand for AEMO? And now that it's gone below 0 in South Australia, what is it that we're doing? And currently, we need to maintain that demand above certain minimum load thresholds, certainly as a whole of NEM perspective. These synchronous generators that have been around for many, many years, they are the ones that are still supporting system security currently. And without load on the transmission network, the voltages float up to the point where it's no longer operating in a satisfactory state. And so we need to have this sort of minimum level of operational demand currently to retain that security of the system. It's continuing to drop across the NEM. You can see the forecast here. This is only going out a few years and getting very, very close to 0 at a whole of NEM picture over the next 10 years. And so how are we going to manage that? How are we going to coordinate that? What mechanisms are we going to put in place? Because at some point, I think it becomes intuitive that if you have more rooftop PV generation pulling out that minimum operational demand, if that occurs across the entire system, you eventually have more generation than you have demand. And while we don't like turning solar off in order to stabilize the system, ultimately at some point that needs to happen. And in times that does happen today under sort of emergency scenarios whereby, for example, South Australia is operating as an island. There are times where rooftop PV systems in South Australia are sort of controlled off through this sort of so-called backstop mechanism. So let's move on to network. A little bit behind time here, that's all right. So here's a view of sort of familiar power system. Pretty simple. Generators, they produce the electricity, feed that into transformers at the generator, step up to high voltage for efficient transport through the transmission network. And these large transmission lines that you see sort of snaking across the landscape, they're very large to carry these extra high voltages, very large currents through to the distribution network and away from these generators. Distribution transformers then to step that voltage down again to the network that you see on the streets around the city, and ultimately to your homes and businesses. The arrow at the end there does look like it's going in both directions, and that's because that's the system of today. We are now running the distribution system backwards at times. You can see that in South Australia example. You can see that in spots around any state in Australia at certain times of the day. And so this is it is today, but it's reflective of where we were. This is the historical approach. So while useful, I don't think it gives us the full picture. For those of you who aren't familiar, how we run as a system, the division of allocation of responsibility for the networks. We have transmission networks owned by a series of companies. We have distribution networks owned by another series of companies. This is ultimately a set of regulated businesses that operate in a deregulated market. So the generation and the retail markets in most areas are deregulated, and in order to carry the energy across those markets, we have these regulated businesses with transmission network service providers, distribution network service providers, and there's some familiar names there. You can see the Victorian ones that I'm sure each and every one of you are connected to. Something else to consider here, though, is as the grid is transitioning, some of these businesses are state-owned and some of them are privately owned. In theory, they all operate to the same regime under the same rules. It's just something to keep in mind about how they might respond to various government policies throughout the transition. Because network service providers ultimately play a huge role in this transition. We work very closely with them at AEMO. In fact, we are the TNSP planner for Victoria, so we do play a role in that regard. But without networks and without the skilled people in those networks, we can't do our job, and we can't make our way through a smooth and efficient transition. So the grid itself is changing, and it's changing in response to what's connected to it. So this is a stylized diagram here of a number of different cases. You can see in the bottom right this traditional base case of, okay, you have poles and wires running down the street and they carry energy to your house. Fairly simple. It's how it's worked for many hundreds of years, and the distribution network has been designed accordingly. It's not designed to be particularly intelligent. It's designed to be robust, easily repaired, cost-effective, and it's not necessarily designed to pass energy back in the other direction, although it certainly can and certainly does. And we see that in scenario 2 here. So in scenario 2, we've suddenly got rooftop PV appears, and it has appeared in abundance, unlike anywhere else in the world. So you now have these power electronic devices called inverters, which are converting the DC direct current energy from these solar panels to the alternating current AC that we need in the power system. And they're starting to flow that energy back into the distribution network. In the third case there, we've suddenly got a few additional assets appearing. We've got batteries, we've got storage, we've got that capability to actually store this energy, when previously the system the supply-demand balance had to equate at any given moment in time. If it doesn't, we have a frequency issue. We're unable to retain that for too long before the system will start to fall apart. And so having storage in the system is really a fundamental part of the future grid. Having it in the distribution system means that the distribution system needs to evolve and modernize in order to accommodate that additional, basically additional complexity, but very much additional opportunity. Because if these challenges happen around the level of reverse flow through the distribution network back upstream to the point where the network can no longer cater for that, well, one way to mitigate that is to use that energy closer to where it's being generated, store it in a battery, and then save that for later when you may not have that abundance of solar into the evening. So these batteries and the complexity of them is a real opportunity for utilizing these assets in a better way, but it does require modernization of the network they connect to. It requires modernization of AEMO's interaction with those networks, and it ultimately is something that needs to be planned for in advance, or else that opportunity doesn't necessarily arise. So that's very, very front of mind for us as well. There's a few other factors that change as you move from one of these scenarios to another. we really, as a system operator, certainly didn't need visibility of what was happening at your house or at that level of the distribution network in order to make any decisions, and really needed the distribution network. They were able to see what the flows through their transformers were doing. They were able to see what the higher voltage or medium voltage parts of their system were doing, and that was fine because they could predict then what would be happening at households. But as you start adding these generators and batteries into the distribution system, suddenly that visibility starts to matter. They need to know, and we need to know to a lesser degree perhaps, how much of that generation is happening in the distribution system. Where is it? What's it likely to be doing? What will it do under adverse conditions? What other capabilities might it be able to hold? And so that visibility aspect is really critical. And we do now operate a register to understand where individual small-scale CER systems are installed around Australia, which is there largely to give us what we do lack to a degree is predictability. So while we don't need to be measuring the output of every one of these devices in everybody's household, we do need to have a rough understanding of in aggregate what are these devices going to be doing? How much are they going to be generating in the next 5 minutes, half an hour, 2 days? And so that predictability and forecasting is really key. And so we do need that data in aggregate in order to make those assumptions. But predictability alone, it can only go so far in terms of the inputs that we can get from solar observations, weather forecasts, wind forecasts. If the generation is effectively passive, if it just operates as per the availability of its fuel source, then that's useful and you can predict that. But if it's operating in a more intelligent way, if it's trying to perhaps optimize the energy consumption of a household by storing energy in a battery that might be behind the meter of that household and stored until later in the day, we're going to suddenly start seeing, and we do start seeing, changes to that demand profile at a grid scale, because we've got now this sort of intelligence and this complexity behind the meter that wasn't there previously. And so the next step is that coordination that I was speaking of before, where we need a way as an industry to coordinate that equipment such that it is visible and predictable and participating and providing values back to those consumers. So last slide here on networks. This is an excerpt from our integrated system plan again, and it shows that, well, there actually is still value in transmission. And while you might think that, okay, we're generating all of this energy behind the meter, we've all got these solar panels on our houses, is that the decarbonisation solution? It's part of the puzzle, but there are still, significant value propositions from large-scale transmission, being that you can then transport renewable energy around the country at scale from really large renewable energy zones, which are a cost-effective way of deploying renewable energy. And it helps as well for geographic separation of weather. Maybe it's sunny in Queensland, maybe it's not sunny in Victoria. Can you now transport that energy at a greater scale than it can be today? And can that help support that renewable energy transition? Can it provide that reliability aspect of being able to move that energy around from various plants when it's needed, especially under situations where maybe the network's not operating as you expect? Maybe there's bushfires, maybe there's an incident like the transmission towers that we saw come down a couple of months ago, not far from my house in Geelong. So this is something that you're welcome to have a look into, and the integrated system plan details exactly where we envisage projects to be needed. And there are varying tiers of that in terms of sort of actionable projects that are able to be invested in part of the regulatory process now, as well as future ones where we see that potential future need. But we also have to ask, well, what else will be needed to make these renewable energy zones, secure and operable part of our system? Because suddenly we're taking a lot of generation and we're concentrating it in a different place. We're no longer concentrating it in these generation centres, such as the Latrobe Valley, such as the Hunter Valley. We're now moving that into, rather far-flung areas at times, and we need this new transmission to carry that energy. But we also need technology to stabilise those zones themselves and to provide the functions that were being provided by the generators in those Hunter Valleys and Latrobe Valleys. So are there additional assets other than the generators that need to go in there in order to maintain a strong system? So we got to the top of the pyramid here. So generation, synchronous generation. I'm sure you're all sort of familiar with some of these photos. These technologies, coal, gas, or hydro. These are when we say synchronous generation, we're talking about large machines, AC generators that are directly connected to the grid, large bits of spinning steel and copper, and they obey the laws of electromechanical physics. It's relatively simple. It hasn't necessarily changed enormously in the decades, if not centuries, and it works. And the system's designed around these, and so they provide a huge amount of value over and above what the energy delivered from them can be, and particularly under times of disturbance where there might be an incident, a line outage, or a generation trip, or a load rejection. These large bits of spinning steel continue to spin. And then through the physics that governs them, they can then deliver, for example, additional current into the system to stabilize voltages in a voltage disturbance. They can take energy from the mass of that spinning steel and return that to the system at times of, say, a generation rejection that then is instantaneously available as additional energy to keep that frequency stable. And we call that inertia. So as these units, retire, as they decommit, these capabilities need to be replaced. It's probably important as well to notice that while we have this focus on, okay, coal-fired generation might be retiring, before they retire, are they going to operate in different ways? Are they going to start to decommit? Are they going to start to leave the market at certain times, at certain periods of the year? It's very difficult to start and stop a coal-fired power station in any kind of hurry. It can take a day or more in order to bring it up to synchronism and be generating at full capacity. And if they're off, they're not providing those services. So even before these plants might retire, they could quite easily start to operate in a different way. And here's a chart showing how that might look. This is again from the integrated system plan. When we say sort of 2 to 3 times faster than anticipated for those retirements, this is talking about genuine retirements, as in the plant is no longer available, the system is pulled apart, the workers go home, and these stations are obliged under the rules to provide some advance notice of that, following the fairly rapid retirement of the Hazelwood Power Station in Victoria a number of years ago. Some rules were made that said, okay, no, advance notice needs to be given so that planning can be undertaken for these retirements. And so we get these notifications. But as you can see, that over time, the announced retirements that are advised to AEMO, they're starting to come forward as the economics of running these generators changes. But what you see in the ISP is a pretty large discrepancy between those sort of announced retirements and what could happen based on the modelling exercises the ISP undertakes. So it's pretty important to note that while we think the retirement dates are out here, we should be planning in advance should those not eventuate over that longer time period. We've got discussion in the media today or over the last few days around the retirement of Eraring Power Station in New South Wales, and whether or not that's something that can happen as scheduled mid next year, or whether that's something that the government's looking at stepping in towards. So these are very active discussions as at today. This isn't a far future thing. I guess that just something to add to that, though, that the coal-fired generation is, in many cases privately owned. They are businesses that are there to provide a return to their shareholders, and if they're operating in a market climate that is not favourable for that, they need to be making those decisions as to whether the retirement date is where it needs to be, or are they perhaps trying to bring that back earlier, or are they trying to operate, as I was saying before, in a way that may cause them to decommit through parts of the day or year. Non-synchronous generation, probably a terrible name for it, but one that gets used a lot. This is inverter-based generation. This is generation that is largely happening at DC and has been converted to AC to match the AC power system that we have. So wind, large scale, small scale solar, batteries, indeed, another one close to my home there in Victoria. These are very large and very small pieces of equipment, but they all have this thing in common where they need to be able to have an inverter in order to provide that conversion from DC to AC. And that inverter can have varying degrees of, I guess, intelligence and varying degrees of capability. There is a contrast still between your average inverter and your average synchronous machine. So in terms of the capabilities that it can deliver back to the power system in order to support its operation. It's expensive to deliver current through the silicon output stage of an inverter. If it needs to deliver large amounts of current, it needs to be large and it costs money. And so typically these inverters are sized roughly the same size as the plant that they're attached to. So that for a 10 megawatt generator, maybe you'd have a 10 megawatt inverter or thereabouts. But that differs from a synchronous machine, where while you would have a 10 megawatt generator to match your 10 megawatt turbine, for any given moment in time, perhaps for a few seconds, that generator can deliver even 5, 6, 7 times its rated capacity in terms of current coming out of it. If that happens to happen during a disturbance, that is very supportive of voltage in that area. So it's not as simple as swapping out megawatt for megawatt. Some megawatts are different from other megawatts. And so how might we use inverters smarter in order to satisfy those needs in ways that don't just require them to be bigger? And there's certainly, there's no silver bullet answer to this, but something that we're looking very closely at AEMO is this concept of grid forming inverters as opposed to grid following inverters. So a grid following inverter will look at the sine wave of the AC waveform of the power system, and it will go, okay, the voltage is up here, I inject out here. It's down here, I inject at that voltage, and it follows that AC waveform, which is fine, works great. And almost all all inverter-based generation on the grid today follows that regime. But during a disturbance, so say there's a spike in voltage or a dip in frequency, suddenly that sine wave gets hard to track. And suddenly these inverters are not necessarily behaving in a way that is conducive to operation of the grid. At some point, they trip off and they stop generating, which under a low frequency disturbance is the opposite of what needs to happen, right? We need them to ride through these faults and continue to generate. But as well, they're not responding in a way that I guess sort of sympathetically responds to the fault. So they're there to continue generating, that's great, but they're not over generating to compensate for that different frequency, at least at that sort of instantaneous kind of millisecond scale. And so this new, not by no means new, but rapidly emerging technology of grid forming inverter allows the inverter itself to maintain a 50 hertz waveform inside its own sort of internal logic, and shape that 50 hertz waveform to meet the changing characteristics of the grid. And that makes it operate in many cases a lot more like a synchronous machine, but again, limited by its current output. So yeah, some interesting new technologies and new solutions that can make this inverter-based generation a lot more valuable, basically, and able to operate at higher and higher penetrations. This is a similar chart to what we saw before, but instead of installed capacity, we're now looking at terawatt hours. So in fact, that's mislabeled, that's gigawatt hours. So we're around a 200 terawatt hour system today in the NEM, upwards of 500 terawatt hours of energy out to 2050. And you can see here what our view of a net zero future could look like. It's wind and solar, taking advantage of this abundant fuel sources, so to speak, that we have in Australia. It's backed up by storage for periods where the wind and the solar is not available, so firmed by that storage, and then backed up in this view by gas power generation, in this case with offsets right out to 2050 at a very small scale at the bottom there, but there because there is that need and that sort of that economic rationale for having something there as a backup. So another thing that's really clear here is the role of consumer energy resources. We're right back to consumers again. That top pale yellow, rooftop solar, other distributed solar, and the purple there, the coordinated CER storage. These are playing a key role in our future energy delivery as well as capacity. So a large wedge of our consumption will be fueled by these technologies. And look, this is our view of how a least cost system could work to meet the decarbonisation objectives of Australia. It's not necessarily a snapshot of the future. It's a prediction of how it could look, and it helps us plan towards that future. But inevitably, the future will vary from what we see here. So something that results from the ever increasing installation of renewable energy on a system is that what we deem the penetration continues to climb. And so that is essentially the proportion of generation that's sourced from renewables at any given time. And it's peaked to date. This is a chart of sort of record high penetration there in green at 72%. So for a moment in time there in Q4 2023, we had 72% of the NEM's electricity being provided by renewables. And just given the dynamics of the market at that time, that's almost predominantly wind and solar. So 72% coming from largely inverter-based generation. Now, the purple line represents something else. The purple line represents renewable potential, which we're referring to the total available energy from renewable generators at any instant in time, given the weather conditions. So how much could that solar be producing? How much could that wind generation be producing? Regardless of whether they are, regardless of whether they're turned on, regardless of whether that energy can get to consumers. And you can see there, I feel like 0.3% is a rounding error, but we have very nearly made it to 100% of the demand of the NEM could theoretically have been served from renewable generation at that point in time in 2023. And that is just enormous. We talk about moving towards a 100% renewable system. Arguably, there's the capacity at the source of generation to do that today. But why isn't that happening? There's a number of competing forces that cause these two lines to separate, and you can see that over the years that separation has grown. At that instant in time, and at the end of the last year, predominantly market forces were why that generation was not online. In that, if the price is negative and you're being paid that price, your incentive is to switch your equipment off. And these wind and solar generators, they can switch off very rapidly, and they do. And so you see the withdrawal from the market of that generation to the point where we end up with a roughly sort of 70% penetration record to date. But okay, under a situation where the price is non-zero and where there is value in generating, what is the next sort of binding limit? We can't necessarily run the power system today at 100% renewables, at 100% inverter-based generation, because we need those capabilities that are delivered today by synchronous machines. Those could be synchronous generators sitting there generating perhaps at a very low level, but still providing those services. It could be synchronous condensers, which are essentially a generator without a turbine, without a prime mover. So they're just a large motor spinning out there in the suitable location that can provide those capabilities without providing that energy output. And so these are the devices that are online at these times, that are needed to be online at those times in order to keep the grid stable. Something to think about with this penetration chart is that the government has set a target by 2030, which is roughly equivalent to 80 average penetration of renewables of 82%. So by 2030, we want to be delivering 82% of the terawatt hours coming through the system in any given year through renewable energy. You can't get to 82% on average without spending a lot of time above it. And ultimately, you can't get there without spending a lot of time near to 100. Just simple statistics to get the average up. So right now, the peak penetration that we have is below what the average needs to be in 2030. So there's a huge way to go. But that said, October 2023, that record was falling 1% a week. So it was climbing 1% a week. So, obviously that's a sign of the time of the year that these records get broken, but pretty impressive nonetheless. Here's another couple of views of what I mean by this. The two charts on the left are a day, these are hypothetical days where maybe there's a lot of renewable availability. In fact, the dashed line there is the demand that's needed to be met, and you can see that at times there's far more renewable availability, so that's the potential. at midday to satisfy all the needs of the NEM. But what happens in the dispatch outcome there is on the right, and you'll see that coal continues to generate throughout the day, and that wind and solar are heavily curtailed, particularly grid-scale wind and solar. And so this is an example of where, for example, that coal plant might need to be online to either provide energy in the afternoon or to provide those system services that we need to keep the grid stable. And so it is, through various mechanisms, kept on because it can't shut down for the middle of the day. It takes a day to turn it back on again. And so you don't get the outcome that you'd expect, despite having, in this case, more than 100% potential. On the right, we see the alternate to that. There's additional renewable availability there. There's batteries. And we have a day where that coal plant can shut down feasibly, and may do so for economic reasons if it hasn't retired. And in this case, in the afternoon, as the sun begins to go down, batteries begin to discharge, gas fills the afternoon gap, and the system runs without coal. And this is not something that has ever happened in the NEM, essentially since the first coal-fired generator turned on. I mean, these are kind of toy examples, but I think it's kind of important to recognise that there are sort of non-energy reasons why the dispatch in the NEM over any given day can be materially influenced. I'll flick through a few of these, but we're getting pretty close to time for the Q&A.
Questions online. So
okay, that's all right. I'll go for another 5 and we'll whirl through this. This is just, I'm taking the advantage here of the podium to share some work that we've been doing around the engineering roadmap. So this is just an example of a challenge that we're facing, right? Like the NEM and the WEM, they're transitioning towards these globally untested conditions, unprecedented conditions, over a whole range of different power system phenomena. And our existing analysis methods, all of the modelling that we learn here in university, they aren't necessarily fit for purpose in identifying the needs of the future system. And universities around the world and in Australia are looking to create new ways of understanding that. We have to do these detailed studies, and sometimes these are very open-ended. And if we don't do them, there's a risk in that there won't be timely enough deployment of equipment in order to meet those needs, the future needs of the system. And this has happened already. So we've seen in South Australia that over that period, sort of 2018, some studies were done that recognised that, hey, wait, we're starting to dip into these operational conditions where there's not enough system strength in South Australia in order to maintain a secure system. A lot of analysis was done to work out how to fix that. New rules, new regulation had to be made in order to fix that problem. New investments needed to be made with synchronous condensers. They were procured, they were shipped here, they were installed, they were commissioned in a relatively short order. We've only got a small handful of years where that happened as on war footing. But the ultimate outcome of that was that gas generation had to continue to run at a higher rate than it would have in South Australia for those period of years. In that case, there was a requirement to keep 4 units online instead of 2. And that can result in directions payments. So we have to pay these generators in order to do that, because it costs them money to run. And that can be to the tune of hundreds of millions of dollars. And so while these devices might be, single digits or tens of millions of dollars to install, if they can avoid these sort of operational costs year on year and accelerate that path to decarbonisation, that's really critical. This is just sort of a picture of, I guess, where the engineering roadmap fits into our suite of products as an organisation. We have the ISP, we have the need to connect the equipment, we have the need to engineer the system in order to be able to deal with these new penetrations of renewables. And ultimately, we've got these sort of 4 pillars that we see that the system needs to abide by as it transitions to renewable energy. Firstly, there's that low-cost energy, just taking advantage of the abundant solar and wind that Australia has to offer. We do need that firming technology, pump hydro, batteries, gas-powered generation with offsets. And we produce reports in order to work out how much of that is needed. We need this new transmission, modernised distribution networks to get this energy where it needs to go. And ultimately, the power systems that need to be capable of running at times at up to 100% renewable energy to get that average up. And that's where this roadmap that we've prepared comes in. It's a bit of a journey of where we've come to. If anyone's interested, each of these sort of squares has a report associated with it on our website. Welcome to have a look. But ultimately, it's a way of future back planning. We're saying, what are the gaps? What are the gaps that need to be filled in terms of activity in order to take us to the situation where we can run at 100% renewables? It's very much an engineering focused roadmap. It's there to look at these sort of technical engineering operational actions. We're using the 100% renewables, I guess, as a sort of light on the hill in order to determine what those actions should be. There's a lot of actions that need to happen after the first time as well, but at least it gives us a way of kind of understanding how to prioritize our work across industry. And there's some sort of monitoring there as well around what are the actions underway, just communicating what it is that we're doing, what that we'd like to do, and what that we need help with. There's a series of priorities that we're working on this year, looking at enabling these high penetrations of distributed consumer energy resources. We're enabling new technologies like grid forming inverters to address these system needs. And we're conducting immense amounts of future power system studies to try to work out those known knowns and those known unknowns and the unknown unknowns. And the last one there around building operational readiness is really about just the processes and the interactions between organisations that need to happen in order to make this work. How do we approach the transition step by step? And we've got a sort of an operational transition program that we're looking at that will allow us to understand, what do we do with these major coal plant retirements before, during, after, such that we can retain that system running day in, day out. And that brings me to the end. I don't know if you've got any questions appearing online, otherwise happy to take them from the crowd. Okay. Do you want to use a microphone?
Well,
just for the recording.
Thank you, Chris. And I think you've achieved exactly what we had hoped for in the first talk, and that's to give us a complete overview and really demonstrate that you have to have that combination of technology and all of the other softer factors as well. Question?
Yes, thank you, Chris, for the great overview. I'm interested in this coordinated CER storage that you have on the charts, which doesn't exist today.
Indeed,
like there's and especially vehicle to grid where people will be driving around with batteries that can actually do the job.
Yeah.
So car manufacturers, battery manufacturers, and retailers will need to put together information to the consumer to be able to explain, hey, I've got the car and it's going to be available.
Yeah.
Is AMO doing anything around creating like API constructs or that sort of thing about what sort of information, normalized information is required so that these can be aggregated across retailers?
Yeah, question close to my own heart. I spent about 2 years looking at EV grid integration at AMO. And look, it's fair to say that that's still emerging. That sort of capability of harnessing the storage within vehicles. I'd say it's at the sort of the pilot stage at the moment, and it's when you think about the complexity that has to occur for stationary assets like home batteries. What if the battery drives out the gate? And so you've now got, while there's a huge opportunity, the number of just, gigawatt hours of storage that you could harness from the predicted vehicle fleet is enormous. It's just that additional layer of complexity to go, where is it plugged in? Is it available to participate in the system? Who gets paid for that? What is the limit at that exact point on the grid that it's connecting to that may actually influence how much or how little it can export? And so there is a bunch of work going that probably moves into the sort of Australian standard space is where a lot of that is happening from the perspective of making sure that devices are interoperable. So there's a standard that's emerging for stationary storage that is also applicable to the likes of vehicle to grid. That really we see those as the kind of foundational enablers to it. If you've got technology that can talk and interoperate, then it's a whole lot easier than trying to deal with these sort of bespoke single point solutions that might all be subtly different depending on the sort of the manufacturer. I can go for hours on this one, but does that help answer your question?
Thank you. We might come back to that afterwards, if that's all right. Given the time, I have a question online. It's why can't more batteries and condensers not supply the strength to the system, given that the energy in revolving metal is not very large, and yet batteries can respond instantaneously.
Batteries can provide a huge benefit, and we see that today with the large batteries that we have on the system. There's some interesting studies that you can find certainly around on ARENA's website, some on our own, around the performance of large scale and small scale batteries under disturbances. And in terms of providing system strength specifically, as opposed to something more like a sort of a frequency response or an inertial response. Certainly capable of, but limited at times by their sort of output rating. As I was saying, if you've got a synchronous machine that can operate, 5 times over its current rating for a short period of time, maybe your battery can be rated as sort of 1.2, 1.5 of its rating. You just need more of those batteries. But certainly we do see the value in batteries and supporting future system strength. There's a new mechanism for procuring system strength, which is quite detailed, but certainly batteries have a role to play in there. So it's not a no, but it is at a point where today we don't have enough of them providing the right capabilities in the right places.
All right. Well, there is one more question, but I think it actually leads on to the rest of the seminar series, and it's around the step change scenario and will it be made on commercial terms? And I think that extends into the rest of our seminar series, that yes, we can do all of this like vehicle to grid. Technically, it's commercially and socially, can we do it? So I'll take that question on notice for a future seminar.
That is a really good question, and I hope you get a good answer.
Yes. Well, thank you very much for participating both in the room and also for close to 100 people online. And thank you again to Chris.
Thank you very much for having me.
Very informative seminar.
Thank you.
Thank you. Lots of yours.
Oh, good. I didn't even see how many people were on here.
Oh, thank you all. I took the liberty of allowing Chris to keep going. It's really